All right, I have to be allowed 2 minutes to embarrass Guy. So to me, and this I'm speaking personally now, I've known Guy since, I think, the late 80s. To me, Guy Steele is Mr. Programming Languages. I've known him since I became active in SPLASH in the 1980s as a junior professor. You may not know, but in the dark ages in 1995, I was chair of SPLASH, and I was on the committees. Guy has influenced the design of many programming languages: Scheme, Common Lisp, C, High Performance Fortran, Java, JavaScript. He has many, many, many publications, patents. He's influenced more programming language designs than anyone else in the field, in my humble opinion. His honors include member of the National Academy of Engineering, ACM Fellow, AAAI Fellow, IEEE Fellow, American Academy of Arts and Sciences Fellow, and the SPLASH-PL Achievement Award. Guy is one of only 2 people that I know who used to serve on the POPL Program Committee, this is in the early 90s, and read all the submissions, making useful comments about each of them during committee meetings. The other person was Ravi Sethi. He is very clever. He is friendly. He is musical. He's creative in computing and the arts. You can tell my jealousy is showing through. He's a great person to know and to be around. We did sing folk songs in a bar in a hotel at one of our SPLASH meetings, a bunch of us. Guy often gives back to the community in professional service, which is also exemplary. For example, currently he is serving as the co-chair of the 4th History of Programming Languages Conference, which is going to be in 2020, and you all should come. It's going to be at PLDI in 2020, and this is the 4th one. So, not going to be any more embarrassing. I introduce to you guys Steve.
Thank you, Barbara. And I should point out that I owe a great deal to Barbara as well for a number of assists over my career. And I will point out that she was the co-chair of the 3rd History of Programming Languages Conference back in 2007, and kindly invited me and Richard Gabriel to give a keynote talk there. Okay, so I'm going to begin with a digression, actually, but this is actually something you can use. My slides have a strange aspect ratio, and they also want to be full screen. There we go. Okay, my slides have a strange aspect ratio. They're not 3:4 and they're not 16:9. And the reason for this is that if my slides are 4:3 but the projector is 16:9, then 25% of the screen is wasted. On the other hand, if my slides are 16:9 but the projector is 4:3, coincidentally 25% of the screen is wasted. And I never know coming to a conference which kind of projector I'm going to get. So these slides are 20 to 13. If you do the math, the optimal compromise is 8 to 3 root 3. So how do we find a good rational approximation to this irrational ratio, 8 to 3 root 3? Well, you expand it as a continued fraction, and it turns out truncations as a continued fraction are very good rational approximations to this irrational number. And the successive truncations, this particular one, are 1 to 1, 2 to 1, 3 to 2, 17 to 11, yuck, 20 to 13 that I can work with. So if you use 20 to 13 with either a 16 to 9 projector or a 4 to 3 projector, you will waste less than 13.5% of the screen. Ooh. And if you can't remember 20 to 13, then 3 to 2 is pretty close. So until the 16 to 9s become completely ubiquitous, here's a hint you can use. Okay, now, Barbara advertised this as me covering 50 years of, like, all of programming languages. I can't do that. And in the time allotted today, I probably couldn't even do it in a month. But a different organizer said, well, just talk about the stuff you've done in the last 50 years. That's still a tall order, but this is going to be a little more of a personal reminiscence that'll still cover a lot of ground, I think, in programming languages. So it was just about 50 years ago. It could have been 50 years ago today. I don't remember the precise day, but it was within about a week of today, 50 years ago in 1968. When I was 14, my buddy Al Swide showed me a Fortran program he had written, and it looked very much like this one. It was on cards, and it was about 10 lines long. And I looked at it and said, wow, what's that do? And he explained the program to me, and I was hooked. And I said, boy, I want to learn Fortran. Now, Boston Latin School had an IBM 1130 in its basement. I grew up here in Boston and got my schooling here. So here's the IBM 1130. This is a computer with 8 kilobytes of memory and 1 megabyte of removable disk storage. The cartridge is that big, but you can carry it around. And in 1965, that cost about $41,000, which would be about $328,000 today. And Vincent Learson was an alumnus of Boston Latin School, and when he became a senior executive at IBM, he made sure that his alma mater had a computer for at least the juniors and seniors to work with. And I was a freshman at the time. But, oh yes, this is the central processing unit and the console printer, and then this funny locked box I think is a CalComp plotter, but I can't tell because the box is locked up. This is not Boston Latin, this is another one that I found on the internet. And then there was this other box that was, yay big. This is used for reading the cards. And the cards went into the silver hopper, and there was a lot of mechanical transport issues. It was like a Xerox machine except with cards instead of printing paper. Okay, so I wanted to learn Fortran. So having been given the clue by my buddy, I went to my math teacher and said, "Can you teach me Fortran?" And he said, "Well, I can give you these books to read." He had some supplementary material on his bookshelf. He grabbed a handful of these IBM booklets, about 50 pages each, on programmed learning. I think he gave me 4 of them. And I took them home and read them all over the Thanksgiving weekend and came back on Monday and said, "Please, sir, may I have some more?" This is great. And he said, "Oh, Steele, I'm going to work out a deal with you. For the first 10 weeks of this year, I noticed that you've gotten 100% on every weekly quiz." And he said, "I will let you spend 4 days a week instead of coming to math class. You can spend your time in the computer room instead. But the 5th day you come and take the quiz, and if you ever get a single question wrong, the deal is off." And that was tremendous motivation. I aced the quizzes for the rest of the year and got time in the computer room. So that was an amazing opportunity. And he was, his name was Ralph Wellings. I really owe him a debt of gratitude. The next year, my new math teacher, Morton Weinert, I asked him could I have the same deal, and he said no. He always said, "No, you need to really start learning the math now. You can't just you can't muscle through this on your own." But for a year, I had the opportunity to learn Fortran, and then I went to downtown Boston, found a technical bookstore with my buddies. There was a gang of us, the IBM 1130 gang, that would hang out together. And I bought this book on Fortran programming. This is a classic book, and I bought this book on using IBM 1130, which taught me how to do assembly language. And then, about 6 months later, the 1969 Spring Joint Computer Conference happened to come to Boston. And we got wind of that, and while attending the paper sessions cost money, the exhibit area was free. So a 14-year-old could afford to do something that was free. And all the different computer vendors had displays, and in particular, IBM was showing off their brand new programming language, APL. And they were giving away these brochures, and I grabbed one, and at the end of the exhibit, just they were closing down the exhibit hall at the very end of the conference, I kind of stood around just to see what would happen. And they had been demoing APL on the selector terminal for 3-4 days, and just letting the fanfold paper drop on the floor behind it. And at the end, they had several inches of fanfold paper. And I watched, and one lady in the IBM booth proceeded to grab the fanfold paper and tore it off and was about to carry it away. And I said, "Are you going to throw that away?" And she looked at me and grinned and said, "It's yours." And I took that stack of fanfold paper, and between that and the brochure, I taught myself APL. Lisp took me a little longer. I got a hold of the Lisp 1.5 Programmer's Manual. That was published by MIT Press, and our IBM 1130 gang also went to the MIT Press book sales to get technical books. And I bought this, and it confused me no end because it gave a definition of Lisp in terms of itself, so-called metacircular interpreter. This confused me no end, and I was convinced that this kind of programming language specification must be completely broken. And this gave me a chip on my shoulder for a couple of years about Lisp, which took me a while to overcome, but I have to admit it, I was down on Lisp for a while. It turns out that it was slightly broken, but not for the naive reasons that I thought. It turns out there were very deep reasons why that kind of definition was slightly broken. John Reynolds wrote a wonderful paper about it in 1972, which was presented at the ACM National Conference, which happened to be in Boston that year. I was able to attend. So I looked out in a number of ways. Things were happening in Boston in the space of 3 or 4 years. Okay, so my buddies and I hung out at MIT. We went to the high school studies program. MIT still runs this great program for high school students, where it's MIT students teaching high school students on Saturday mornings. And I took a nice course in group theory. That was nice. There were some programming courses, and if you took a programming course, then you got access to IBM 1130s at MIT. Oh boy, more computer time. And then we discovered, I'm not sure, we just kind of spread this by word of mouth, it turned out that the doors to the MIT Artificial Intelligence Lab and to its Project Mac were unlocked. Anyone could walk in off the street. As long as you kind of looked like you belonged and didn't cause any trouble, things were fine. So there were technical reports, and I got all the technical reports on all the artificial intelligence work. I was 15 at the time, and read and understood as much as I could, which wasn't a whole lot. But it also gave us access to a PDP-10 computer. This had 100 times the memory of the IBM 030, had a megabyte. And it was about $1 million computer, and a high school student could just walk in off the street and start using it. And as long as you didn't bug anybody, it was okay. This ended a couple of years later when the Vietnam War protests started. And there were some credible threats that some vandalism would be done to computers once they put locks on the doors. Whereupon my buddies and I got pretty good at tailgating. Again, we tried really hard to lay low and not cause trouble. And through here, I got access to MIT's Lisp documentation and source code that they were using in the laboratory. And studying that, I got over the hump of not liking Lisp. And Digital Equipment Corporation had a field office. They were the manufacturers of the PDP-10. They had a field office in Central Square, about 4 blocks from the MIT labs. And they were okay with high school students walking in and taking free manuals, and I would take them home and study them. And so I had access to information that I never realized how unusual that was, but it was a great opportunity for me. So to make a long story short, in 71 and 72, my last year and a half at Latin school, I implemented Lisp on the IBM 1130, basing my design on MIT's MacLisp. But I added a string character type because I thought, well, there really ought to be strings in this language. And so I did that. I did a bunch of other small projects and just messing around. I also learned COBOL and wrote some COBOL code for actual cash money. And in May 72, when I graduated, my parents said, you're not going to sit around the house all day, get a job. And so I went out, and I didn't really want to work at McDonald's or anything like that. And I applied for some key punching jobs, but nobody would hire me because I wasn't 18 yet. And finally, by word of mouth, again through the gang of computer people based at Boston Latin School who hung out at MIT, one said to me, we heard that Bill Martin is looking for Lisp programmers. This is Professor Bill Martin at MIT. So I just casually dropped into his office one day in July and said, I heard you're looking for Lisp programmers. I'm just, really almost this tall, but real skinny and not much to look at. And he looked at me and said, okay, you have to take my Lisp quiz. And he pulled a sheet of paper out of his desk and said, go over there and spend 2 hours with that. And so there were some programs to write and some puzzles to solve, and I wrote it all out. And when I was done, I gave it back to him, and he looked it over gravely, looked at each page, and then said, you're hired. Whoa! Okay, so I found a job working at MIT. I, in fact, had chosen to go to Harvard University as an undergraduate. So I had what I now realize was a really rare opportunity to be affiliated with 2 universities at the same time. I was taking all my classes at Harvard, and I was working part-time at MIT during the school year and full-time during the summer. At Harvard, I set out to be a pure math major because I'd loved math all my life. And that was where I hit the wall. I discovered I really wasn't very good at pure math, particularly continuous math. The infinite dimensional Banach spaces did me in. So I switched to applied math. Fortunately, I'd already taken a computer course. It was easy to make the switch, and I took a lot of great courses. And my best memories of Harvard are the non-computer courses. The economics, the Western Civ, the Latin poetry. That was all great stuff. And I spent a lot of time in the basement of the Lamont Library because I didn't have enough money to actually live on campus. So I lived with my parents, 3 miles away and commuted. And but while I was on campus, if I had 2 hours between classes, I didn't have a dorm to go to, so I'd go to the library. And after I'd finished my homework, what am I going to do? Okay, well, what's in the library? Well, they've got back issues of all kinds of journals. So I read all of Martin Gardner's recreational math columns from Scientific American, going all the way back to the beginning, so that was cool. When I was done with that, what else did I read? Well, I found the communications of the ACM. And said, okay, why don't I work my way backwards through that? So from 1972 to 1947, I kind of worked my way through that and looked at all the technical articles and didn't understand most of them, but at least tried to read the abstract of each one, and the ones I could understand, I read. And by the time I finished Harvard, I'd sort of read 25 years of computing. So that's one way to spend your spare time if you don't have any friends. Okay, and then from 75 to 80, I was a graduate student at MIT in computer science. Okay, so that's quick background about my early schooling, getting into college and grad school. But I had the opportunity to be involved with computing before I got into college, as it turned out. So here's a list of some projects I've worked on. I'm not going to go through this list now because I'm going to devote about 1 slide to each of these just to give you a quick idea of the kinds of things I've worked on. But they were done in a number of institutions. MIT, spent a couple of summers at Stanford University, worked at Carnegie Mellon University, and then in a succession of industrial research laboratories. Okay, so I was hired by Bill Martin at MIT in 1972, and he put me to work maintaining the Lisp interpreter. Lisp was the workhorse programming language for the AI lab in the Maxima group. Why Lisp? Why not C or Pascal? Well, those didn't exist yet. PL1 was available, but hadn't been implemented for the PDP-10, which was their workhorse machine. Bliss was available, that had been invented at Carnegie Mellon, and there wasn't a lot of portability of research languages among universities at that time. In fact, while both CMU and MIT both used PDP-10s, they used different incompatible operating systems. And so software really wasn't portable between the two universities. So in the case of MIT, it was Lisp. And so I gradually took on the maintenance of the interpreter runtime. John L. White, who had been maintaining everything, focused on the compiler, and I learned a lot about compiler design from him. I implemented several major enhancements to Lisp. I designed a binary file format, which hadn't existed yet, wrote a linking loader, completely rewrote the storage management and implemented a new garbage collector according to the design that John L. came up with. I completely wrote the I.O. primitives and made those I.O. primitives portable to 6 different operating systems on the PDP-10. So actually Lisp became one of the first languages that was easily portable to several different PDP-10s, and it spread to Carnegie Mellon and to Stanford and to other places. And it was through that collaboration with Stanford that I got to work closely with Richard Gabriel, who's been a lifelong colleague of mine. And John O. White and I collaborated on language design decisions on Lisp. Okay, I had also been reading Knuth's Art of Computer Programming, which was just coming out then. And in the first volume, he had mentioned an open problem, which is, design a parallel garbage collector so that one processor can be collecting the garbage and managing the storage while the other one is doing the work. That seemed like an interesting problem. And I already had some GC experience working on the Lisp interpreter. And so this problem was cooking in the back of my mind. And the summer of '74, Buddy and I went over to Europe and did the student Eurail pass thing and went from city to city and stayed in hostels and saw art museums and stuff like that. But the question was how to spend the time on the train. You can only do the scenery for so long. So I couldn't let go of this problem. I ended up working out the complete algorithm while riding on trains in Europe. And when I got back home, I wrote it up as a paper, and it won the ACM Forsyth Student Paper Award. Whoa, wasn't expecting that. And I've got two distinct memories of this. This is actually one of the very few projects that I worked out entirely on my own. It's also one of the very few papers which I had to publish before again because I had a severe mistake in it. And the moral there is more eyes catch more bugs, and working in teams can avoid these problems. The other thing that happened is that once this paper was published, people started regarding me as an expert in garbage collection. I felt very funny about that. I'm just a student, I've only published one paper, but journals started sending me garbage collector papers to referee. And I finally decided that was okay because in the course of writing this paper, I had read every other paper I could find in garbage collection, every other paper in literature, of which there were about 30. Didn't take that long. Having read those 30 papers, maybe I was an expert on garbage collection. I don't know. So I did my best and put in the work. Once I got into graduate school at MIT, I was collaborating with my thesis advisor, Gerald J. Sussman, and we designed a language called Scheme, which turned out to be a dialect of Lisp. It was designed to be the next great AI programming language. Carl Hewitt, who designed an AI language called Planner, was kind of a fear-improving based language. And in response, McDermott and Sussman had produced another language called Conniver, and the name of the language is clearly a play on words. And then Sussman and I were trying to understand Carl Hewitt's response. There's actually this kind of back and forth between Hewitt and Sussman. It was very, very entertaining to watch. So Hewitt had this new theory of actors that turned out to be related to object-oriented programming at the time, languages such as Simula and Smalltalk and eventually Java. And Sussman and I thought we were going to construct the next language. We called it Schemer, Planner, Conniver, Schemer. But the operating system, PDP-10, only allowed 6-character names, so we had to leave off the R, and that's why it got called Scheme. So we tried to embed the actors, these objects that can send messages to each other, within a small list. Sussman thought it would be a good idea to use algol name scoping because he thought that would make the actors come out better, which was different from what other lists had done at the time. And much to our surprise, once we finished the implementation, we observed empirically that the implementation of actors and the implementation of lambda expressions had identical code. That was a surprise to us. We actually thought they were implementing different behaviors, but they turned out to be identical. And so we concluded that if they have identical implementations, they must be the same thing, and that led to a series of papers. We also realized that our little lists could execute denotational semantics directly. Denotational semantics were a way of describing programming languages essentially in terms of Church's lambda calculus. And what we ended up with Scheme was essentially a practical interpreter for the lambda calculus. And we could take all this theoretical stuff, literally feed it into programs, and it would execute it and give us the answers. And for my master's thesis, I wrote the first scheme compiler. And I think his big contribution was being the first compiler to use the continuation passing style as an intermediate program representation for a compiler. And some other people have copied that idea since then. So I've hardly worked on Scheme at all since 1980 when I graduated, but other people have picked it up and it's turned out to be a successful language. I felt really good in the 1980s and in the early 90s when people started citing our papers in the OPL conferences and the Lisp conferences and so forth. And then they stopped citing our papers, and I realized we've really succeeded. They're still using Scheme, they're just taking it for granted as part of the infrastructure and not bothering to cite the papers. And that's when I knew the Scheme was a success. And since then, Scheme has tailed off and Haskell has taken over in some ways, and there's this life cycle for languages. Okay, I worked on Emacs, the text editor, in 1976, and that was, again, something I kind of fell into by accident. The text editor we used primarily for writing programs was called Tico at that time. It was a sort of a character-time editor, and you type in a cryptic string of commands, then hit 2 alt modes, then it would execute the string, and modify your editor buffer and show you what that window in your program looked like, and then you'd repeat. But others, I think Carl Mickelson was one of them, had added a rudimentary real-time editing mode. What you see is what you get, where as you type the letter A would actually appear on your screen right away, and where the cursor is. Wow, what a concept. These were the early days, we were just beginning to work out these ideas. And Stallman generalized this implementation. It had a dispatch table, and as each keystroke was read from the keyboard, it would look it up in this dispatch table and do what the dispatch table said to do. Stallman said, why not just let every entry in that dispatch table be a Tico macro? Suddenly, every keystroke was completely programmable. What a powerful idea. And immediately, 4 different people within the labs created packages of useful extensions. And each of them gained certain adherence, and this completely disrupted our pair programming culture. We were accustomed to being able to help each other keyboards, and it was not unusual for me to sit down next to somebody and say, I'm having trouble with my Lisp program, and I'd say, okay, let me grab the keyboard for 5 seconds, type something, and, whoa, this editor isn't the way I want, which package are you using, oh no. So I set out to reconcile and regularize and standardize these extensions. I got a pad of paper, I interviewed the original package creators, I created big tables of commands and tried to make them regular so that, for example, if meta T transposed words, then control meta T would transpose S expressions for Lisp, and control T would transpose characters, and similarly for going forward and backward and so forth. And Dave Moon and I began to work on a linking loader for these packages so it would be a little more modular. And as soon as Stallman saw what we were doing, he jumped in and ran with it. He could program 10 times as fast as Moon and I put together. And so at that point, I was actually happy to let Stallman run with it, and I returned to working on the Scheme compiler. So I worked on Emacs for about 3 months and got the project kick-started. I helped to sort of work on the design of it, but Stallman deserves 99.9999% of the credit for then implementing it, spreading it, putting a Lisp into it, Emacs Lisp, and making it a widely used package. Not the only editor, but it's the one I still use today, partly because it's got a Lisp in it now, it's very convenient. Now you can see that Lisp is actually figuring very strongly in my life, despite the initial animosity I've had. I said I spent 2 summers working at Stanford University. I had an opportunity to work on a project that it was a new supercomputer being designed by Stanford and Lawrence Livermore Laboratory. This is an audacious project. They wanted to have 16 processors and 1 gigabyte of memory. And in 1980, that gigabyte of memory cost enough money that briefly this project was actually a line item in the US national budget. They needed a pile of money for this memory, and they eventually did build it and used it for some things. But for applications, they wanted both numeric and symbolic computation. And therefore, they wanted Lisp for sure for the symbolic computation. They also needed numeric language. They didn't go for Fortran, they asked for Pascal, which by that time was sort of a hot new language. And so I worked on S1 Lisp with Richard Gabriel and Rodney Brooks, and we had a paper on it at the 1982 Lisp and Functional Programming Conference. And it was kind of interesting because the Lisp compiler people, that was me and Richard, and the Pascal compiler people got into friendly competition. The S1 was kind of the last of the grand non-RISC computers. They had very complicated addressing modes. And it was just after that that the so-called RISC style, where you just have load and store instructions and everything else gets done in the registers, lots of registers, that style came into vogue. And so we competed to see which of the 2 languages could use those very complicated addressing modes more effectively, and it turns out the Lisp won out. Because because it turns out that in Lisp it's very easy to write pattern matching things, and we can pattern match the various addressing modes against the parse tree of the program being compiled, and make effective use of that. So in building this S1 Lisp compiler, we integrated techniques from the Mac Lisp compiler, but also techniques from the Bliss compiler at Carnegie Mellon. That was a very different C-like programming language. But the Bliss compiler had really novel ideas about register allocation. We were able to adapt those ideas about register allocation from that language and make them work on Lisp on this completely different architecture. We got a paper out of that with the symposium on compiler construction. So that was fun. And Bliss will play another role later in this talk, so I'll mention that language. Okay, so I graduated from MIT and took a job as an assistant professor at Carnegie Mellon University, and started teaching classes, and really enjoyed teaching classes. And Pete's me wishes that I'd stayed in a university career teaching, but that's just not the direction things went, and I'll explain why in a minute. But at that time, most Lisp implementations and their compilers were being funded by DARPA. And DARPA observed there are a bunch of different dialects of Lisp out there, and we feel that these are redundant and our money is being wasted, funding too many diverse projects. So, but we noticed that Interlisp runs on a different bunch of machines, so if everybody would write all their code in Interlisp, then it'd be a lot more portable. And all the people who had been used to using MacLisp did not like that, because there are very strong differences of philosophy between the designs of MacLisp and Interlisp. This is kind of a political thing. And so Dick Gabriel went around and talked to the technical leads of the various MacLisp offshoots and persuaded us all to cooperate on a concept, on a common standard. And this actually took a while to persuade people to do it. So there are two Lisp machine companies, Symbolic Sync and Lisp Machine Incorporated. At Carnegie Mellon, Scott Fallman and I had started a Spice Lisp project. It was kind of a version of MacLisp designed to run on personal workstations of the day. There was S1 Lisp that I was involved with, and MIT had a new project for Digital Equipment Corporation's VAX computer, and they were trying to implement that. So eventually we came to some commonality, and we ended up calling Common Lisp because we couldn't think of a better name we could all agree on. Yushang Lisp was in the running, but we just couldn't all agree on that. And there was a committee of about 30 people representing all these different things, and as you know, design by committee is really hard. It's hard to get consensus. So I did not chair that committee, but I volunteered to edit the document because nobody else wanted to do that. And I volunteered to coordinate communication. And so I ended up spending a few years managing multiple rounds of discussion and voting by email, something like 3,000 messages went into the design of Common Lisp in the space of about 3 years. And I integrated all the changes into the draft specifications and issued like 6 or 7 draft specifications. We finally published a paper at the 1982 LFP conference, and it had 30 people authors. I think you can idea the size of the committee. And that final specification was finally published as a book with Digital Press. And I just volunteered because I was just trying to help everybody out. But it turns out that the royalties from that book actually made it possible for me to move back to Boston. I provided just enough money to be able to afford the down payment on a house here, because housing prices were higher in Boston than in Pittsburgh in those days. Okay, but I'm getting ahead of myself. Anyway, so sometimes when you volunteer for something, something good falls in your lap. Sometimes when you volunteer for something, it turns out to be a bunch of work. And all that happens is that you learn from it. That's fine. And sometimes you volunteer for something, and it turns out to be terrible. I can't predict. This piece of volunteering turned out to be pretty good. Okay, now back to Bliss. One of the reasons I had taken the assistant professorship at Carnegie Mellon University was specifically because I wanted to work with Professor William Wolf. Bill Wolf knew how to build optimizing compilers, he and his team of graduate students. I've been very impressed with his work on the Bliss compiler. They'd written a book about it that I devoured, and it was from that book that I learned the register allocation techniques that I'd used in S1 Lisp. The subsequent project was something called PQCC, the Production Quality Compiler. And their goal was if you could write a sufficiently high-level description of a language, like its grammar and some of the semantics, and a high-level description of a machine, then you could put it into this framework, turn a crank, and out would come a compiler. And if you had multiple machine descriptions and multiple language descriptions, then you could make many compilers with not much overhead. So that was the dream of PQCC. And I wanted to learn that technology. So I came to CMU, and just as I came to CMU, he left to spin off a startup company. So fine, he formed a compiler company. And so I taught, I worked on Spice Lisp and Common Lisp that time. But 2 years later, I still really wanted to work with Bill Wolf. So I found out that I could take a leave of absence from CMU, and I joined Tartan Laboratories. And I worked on the code generator framework for their commercialization of PQCC. thing that happened along the way is we discovered that we were trying to write the description of the C programming language, discovered that C wasn't very well documented. I mean, the standard Karen and Ritchie book, the programming language, C rather, was a really great book for programmers. It kind of covered all the normal things you want to do. But a language specification for a compiler writer has to cover all the screwy cases. And all those screwy cases weren't written down. And so Sam Harbison and I set out to do that. And the result was a book, C, a reference manual, which we published with Prentice Hall. And I worked on the first edition, and then after I left Tartan, Sam kept working on it. It's now in its 5th edition, so he's kept that book going. It's still in print. And I still haul it down once every couple of months myself to look up some fine point to see that he's documented. Okay, so that was my work at Tartan Laboratories. I learned about compilers. And I was just completing 2 years at Tartan Laboratories, and I was facing a decision. Do I stay with Tartan Laboratories and continue to work with Bill Wolf, or do I return to Carnegie Mellon because they would only hold the professor slot open for 2 years, so I took the leave. So I either had to return or give up that slot. And just as I was having to make that decision, Danny Hillis, who was a graduate student at MIT that I known when I was a graduate student there, showed up at Carnegie Mellon and gave a talk. Because while I was at Tartan, I still attended talks at CMU and occasionally gave a guest lecture myself, because I wanted to stay involved with that community. And Danny Hillis came and gave a talk about a weird new parallel computer he was working on called the connection machine. And the idea was you would have as many processors as possible, and in order to do that, you'd make the processors as small as possible. In fact, they were 1-bit processors, and each one had 4,000 bits of memory. You thought 8 kilobytes of memory is small. This is 4 kilobits of memory per processor. And so whenever you wanted to do arithmetic, it would have to be bit serial. But the point is, he was trying to do marker propagation algorithms of the kind developed by Scott Fahlman when he was at MIT before he went to CMU. Notice all these names that I keep crisscrossing and coming across time and time again. Danny Hillis came and gave a talk, and he talked about the AI uses of this machine, and then he said offhandedly, but of course, this is a bit serial machine, this will obviously be no good for numerical computation. Well, by that time, I thought of myself as a hotshot coder, yeah, right? But telling me that I can't program a computer to do X is like waving a red flag in front of a wall. So I said, okay, well, sure, it's going to be hard. Let's find out how hard. And so while he finished his talk, I did some back-of-the-envelope calculations on a piece of paper I had written. And yeah, if you're going to do bit serial arithmetic, then if you're going to add 32-bit numbers, then it's going to take 32 cycles. And if you're going to multiply them, well, let's say they're floating points, so it's 24 bits by 24 bits, and it's bit serial, so that's 576 bit combinations, that's 24 squared, to do. And then you've got to deal with the normalization, you've got to deal with the exponent computations. And let's see, what did he say the cycle time of that machine was? Oh yeah, 7 megahertz. These could process about 7 bits per microsecond. And when you work it out, yeah, a multiply is going to take about a millisecond. That doesn't sound great. And an add was going to be about half a millisecond when you worked out all the details of that, because you have to align and shift and all that stuff, and you have to use the serial orders for that. But then when you multiply by 64,000 processors, you're up in the range of a Cray 1 supercomputer, which is the big supercomputer of the day, almost 100 million operations per second. So after Danny finished his talk, I went up and said, "Hi, Danny, good to see you again." Said, look at this calculation. This so-called non-numerical computer is Cray 1 class. And he looked at me and said, "Could we have dinner tonight?" Okay, so it's just the accident of my showing up for his talk that I ended up getting hired by his Thinking Machines Corporation, and I moved back to Boston at that point. And royalties from this book helped me to put a down payment on my house and made all that work. So while I was at Thinking Machines Corporation for almost 10 years, I was a director of system software development for Thinking Machines. And so I supervised the development of 3 parallel programming languages for them: Connection Machine Lisp, C*, and Connection Machine Fortran. And in all of these 3 cases, the idea was to have the same code operate on many data items at the same time. We had this highly parallel machine. We were going to have, operate on 64,000 things at a time. So the emphasis is on getting lots of data in the machine and executing the same code on the different data items. You might think it was a database machine. Curiously, Thinking Machines never really got into database work. They focused on scientific computation. So the idea was to have the same code operate on many data items at the same time, and yet try to integrate that idea with the existing distinctive style of a host language, Lisp, C, or Fortran. And so this is the challenge of the language design, to take a new idea and not just bolt it on the side, but to integrate it with the flavor of the language so it formed a cohesive whole. And we ended up doing this in 3 very different ways, and that, I think, was the interesting challenge of my work there. And I also emphasize that data parallelism is a software style Some people said, isn't that the same as SIMD? I think if SIMD is a hardware style, it really means literally a hardware processor fetches one instruction and applies it to a bunch of data. But in fact, the data parallel style can be used on non-SIMD hardware, can be used on distributed clusters and things like that. And it's a software style that can provide portability among different styles of parallel computer. And Danny and I published this article, Data Parallel Algorithms and Communications of the ACM. And that has turned out to be my most cited paper that doesn't have 20 co-authors. It's got about 1,200 citations at this point, so that had some influence. While I was there, I also did some other writing for thinking machines. I just like writing. And so I wrote technical summaries for the CM2 and the CM5 systems, which covered both the software and the hardware, as well as libraries and stuff like that. Okay, so connection machine Lisp. This is co-designed with Danny Hillis, and Skeff Foley did most of the implementation. And the idea is, think of it as being like APL. It's an array processing language, but imagine that the array positions are named by symbols instead of numbers. They're named by Lisp data structures. And there's an emphasis on primitives for permuting and reducing data. In effect, we were doing MapReduce before MapReduce was a thing. And floundering around and really not understanding, how to use it, but trying to make languages that would embody this goal. And we had papers on this. And I just put a fragment of code there so you can get an idea of what the language looks like. I don't expect you to actually read the code. This is a prime number sieve, and you'll see prime number sieves on the next two slides as well. But notice the use of this little alpha character here and this bullet character here. Essentially, alpha means do the following code a bunch of times. And the bullet says, except here, this is already a vector that is spread out among the processors that already has multiple items of data. And that was sort of the general idea of how we integrated that to Lisp. And you can read the paper about it in the conference if you want to know more about that particular language. C star, I did much of the design. John Rose did much of the implementation. In fact, John Rose, I think, did almost all of the implementation. He then went on to have an illustrious career at Sun Microsystems and now Oracle as a senior technical lead on the development of Java programming language. So yeah, he's done wonderful work on keeping the development of Java on track. He works with Brian Getz and a couple others. So the idea here was that we could take some C data structure. It could be an int or it could be a struct, typically a struct, and we could declare it to be poly. And that just meant whenever you declare one of these things, instead of just getting one copy, you get a copy in each processor. So I can make a record structure like an employee record, and then say poly struct employee database. And the database would actually, in effect, be a big array, one element per processor. And the key insight here is we were able to use the compound assignment operators already existing in C to express communication and reduction. So, and it just had to do with which processors you were indexing. So if you're indexing an array and we send something from array location 26 to array location 37, then down in the machine, processor 26 will be sending something to processor 37. And moreover, we did compound assignment of a bunch of processors, all tried to do a plus add into processor 3. And processor 3 would receive, in effect, would add into its copy, its integer or its floating point number, the sum of all the things that have been sent to it during that assignment statement. And that was handled by a particular piece of hardware on the connection machine. In fact, corresponding fairly directly to that. The other thing we managed to do was to allow the use of almost all C control structures, despite the fact that it was implemented on SIMD hardware. And we had this theory of, oh well, if there's an if then else, and some of the processors will go this way and the others will just have to wait. And then when these processors have done this piece of code, then these processors can go down the else branch. And then when they rejoin, you unite them into a single cohort that's all marching together again doing the SIMD thing. So that provided a SIMD implementation of what doesn't look like a SIMD language style. And then later, when we implemented it on MIMD machines, that has where each processor had its own instruction stream, then in fact you got better efficiencies because you didn't have processors waiting for each other. And then the third one, connection machine Fortran. This is essentially all of Fortran 90, which had a few features for parallelism. Plus, there's a feature that had been proposed for Fortran 90, but left out called the for all. They were afraid it was too complicated. And I thought, aha, for all is actually the key to getting good performance on the connection machine. So I specified that would be added back into the language, and we would also add some data distribution declarations. We then subcontracted the development of this language to Massachusetts Computer Associates, which was a commercial company whose thing was developing Fortran compilers. And so I was able to collaborate with their team, and these are some fairly well-known people in the field: David Loveman, Kathleen No, John Lucas, Eugene Albert. And I collaborated with them, and I provided sort of the hardware expertise on the connection machine. They provided Fortran expertise, and we produced some actually fairly good Fortran implementations for that. We got several papers out of that as well. And this is what the Fortran, this is what the prime sieve algorithm looks like in connection machine Fortran. Okay, so you'd think that would keep me busy at Thinking Machines working on these 3 languages. But in fact, Common Lisp didn't stand still. There was a Common Lisp community, and Thinking Machines had an interest in Common Lisp because, in fact, they used Lisp as an implementation language. They were using Symbolic's Lisp machines for a lot of their infrastructure development. So Thinking Machines also delegated me to be the representative to the Common Lisp Standards Committee for X3J13. And the idea is to make an ANSI standard. And there was some politics going on there too. There were some threats that that the European Standards Organization might make an ISO Lisp. And we didn't want to, Americans didn't want to be forced to use a European Lisp. And it's not because it was European, just that it was different from what they were used to. They didn't want to have to re-implement everything. But they knew that once there was a standard, then there would be pressure from bureaucracies above to use the standard thing. So the only out was to make, well, we need to standardize this other one too, so it also qualifies as a standard thing. So I volunteered to be the vice chair of the committee and to do a lot of work. And I prepared a 2nd edition of the Common Lisp book, but it became obsolete because the committee continued to invent new features. So in fact, the Common Lisp standard is actually rather different what appears in that book, although the book is still useful. And when the chair, Bob Mathis, eventually resigned, then I became the chair because I was the vice chair and I got to run that committee for several years. And it was like herding cats. In particular, at the end, we spent 6 months on a letter ballot whose sole subject was who deserved to get thanked for what. The politics is that bad. And we had a very contentious meeting, and people said, oh, we don't want to, and I said, just thank everybody all around. I said, no, we don't want to sort history by thanking this person for doing something they didn't do. So I held it. The answer was, we can't possibly sort this out face to face, we'll do a letter ballot. And I did a letter ballot, I went through the protocol in the end, everyone proclaimed themselves satisfied that due process had prevailed, and we were able to publish the standard 6 months later than planned. Okay. Another spin-off of my work at Thinking Machines was High Performance Fortran. This is a committee led by Ken Kennedy and Charles Coble out of Rice University. Ken was very well known for his work on Fortran and for his work on parallel Fortran, in particular Fortran D. And before that, on various optimizing Fortran compilers. And he noticed that there were several different Fortran dialects for parallelism popping up, and he proposed to standardize. It's a very common activity in the field. Once you've seen 3 or 4 experiments or having some success, you try to merge them and see if you can make something that has all their strengths. And so you want to aggregate Fortran D and Vienna Fortran and connection machine Fortran. And in this language, the focus was on developing distribution directives and some new intrinsic functions. So here's an example here, and it's pretty much straight Fortran. It's got a pretty normal Fortran do loop that is nominally sequential. But there are these directives here that say this array should be distributed in block fashion. Actually, the first dimension should be distributed in block fashion across the processors, and the star means the second dimension is entirely within a processor. And there are different ways that the programmer is specified to break up the array across the processors so as to best facilitate inter-processor communication, or to avoid inter-processor communication for data that's tightly coupled. And then this other example alignment here says, well, whatever way you laid out A, lay out B the same way, so that elements of A and B will tend to correspond and be in the same processor. So that was kind of the idea. And then there were some intrinsic functions for doing things like parallel prefix operations. And this was about 3 years worth of meetings, and I flew down to Dallas-Fort Worth about 3 times a year. We'd stay in the same hotel, and we would have dinner at the same Chinese buffet, and just, for 3 years. And the result was a book that's published in MIT Press, yay, with 5 co-authors. I'm sorry, I was one of 5 co-authors. And the others were Mary Zosel and Charles Coble and Rob Schreiber. And it's terrible, I'm blanking on the 4th one. I'm not going to try to take time to remember at this point. Okay. So those are all the things I did at Thinking Machines Corporation. So just working on one company, I had a chance to work on 4 or 5 very different language projects, just because, partly because I volunteered to do stuff, and partly because I had a broad background. Then I came to Sun Microsystems because Thinking Machines went Chapter 11 all of a sudden. That happens to startups. You think they're spinning along just great, and then poof. So I went to Sun Microsystems Laboratories, and one of the reasons I went there is because Bob Sproul, who was the head of laboratories, said, would you like to come here and work with me? Now, Bob had been at Carnegie Mellon University, and we had been neighbors. Our houses had been 4 doors away from each other back then. And so again, just knowing people helps. So I feel very fortunate that Bob took an interest in my career and said, you, come here, this will be good for you. But once I was there, I really wasn't sure what to do. And Bob gave me some space, and I kind of cast about trying to figure out what I should do. That was about the time that the famous Intel Pentium division bug came out. There was a bug in the hardware. And in extremely rare cases, the floating point divide instruction would give the wrong answer. And I thought that was interesting, so I studied that and came up with a new testing strategy and talked to the developers of the Spark processor at Sun to make sure that this bug would not affect their divider designs. And I wrote a paper and actually got a patent over that. And then there's a programming language developed there at Sun by John Osterhout called Tickle, which is kind of a command, Unix command language kind of thing, but augmented. And I wrote just to understand Tickle, I decided to see if I could compile it to C to make Tickle programs run faster. And I developed a Tickle to C compiler and wrote it in Lisp. This took me a couple of months to prototype. And when I was finished, then I got on the internet and looked around. I mean, there were search engines available then, just barely, and learned that there were already 2 companies that were commercializing the Tickle compilers. So I decided I couldn't compete with that. I was too late in that game, so I abandoned that. And I studied other lab projects, including Tickle and another language called Oak, and I looked at Oak and said, oh, it's kind of a stupid version of C, this will not read anywhere. But then the next year, Bill Joy said, Oak has been renamed Java, and we want to put some money behind it. But James Gosling just has this kind of sketchy description language. We need a complete specification. I understand you've written language specifications before. Will you help me? And so Bill Joy and I spent a year writing the Java language specification. That became a book, and it's still in print. It's like in its 89th edition. I want to be very clear. I did not design the Java language. The Java team led by James Gosling did that. But I did help to simplify it. I persuaded James to take some things out of the language to make it easier to write the book. So, for example, the treatment of method dispatch was fairly complicated because of the way the primitive types worked. I said, if you organize the primitive types into this kind of hierarchy, it would kind of match what's going on in the object hierarchy and make the description simpler. That kind of thing. And the Java language had the C comma operator, and I persuaded him to take that out. I said, it pulls its weight in the C language because of the macros. But Gosling was adamantly against ever putting macros in Java, and I said, well, then you don't need the comma operator. And the main place is used in the for statement, and we'll deal with that another way in the syntax. And we'll save the comma operator for something else. And 20 years later, it's a good thing we saved it because now it can be used for expressing tuples and things like that. So we saved some syntactic space for a different language feature. We're not using it for what C had used it for. Okay, from 2003 to 2012, Sun, and then subsequently ordered, Sun bid on a DARPA-funded contract to develop a petascale system for high productivity. This is a high productivity computing systems project. You can look it up at DARPA. And they said, we want you to bring all your craziest programming language ideas that will make high-end scientific programmers not only write very fast programs, but be very productive in writing those programs. And so 5 different companies got initial contracts. Those were winnowed down to 3 and then down to 2 under the terms of the competitive procurement. The 3 were IBM, Cray, and Sun. And those developed into the Fortress language at Sun, the Chapel language at Cray, and the X10 language at IBM. And all 3 of those languages are still kicking around, although Fortress is essentially gone fallow. So the strategy that my team at Sun was to have 3 key principles in language design. First of all, we decided we want to have a mathematical syntax. Most of these programs are going to be written by mathematicians and physicists and engineers. And we thought, when they are talking to themselves and writing sketches of programs down on the whiteboard, they aren't writing C or Fortran or any of that. They're writing a mixture of mathematics and ad hoc stuff. That's how they communicate with each other. What if our slogan were, run your whiteboard? What if we could make the actual programming language look as close to what they're using as their language of communication among themselves? So that was the first goal. Could we achieve it? Not sure, but that implied being able to support at least some kinds of mathematical syntax. So we fully embraced Unicode. We fully embraced some kinds of two-dimensional notation. Secondly, we decided the language would be parallel by default. We purposely made it a little hard to get sequencing, and we made it a little bit hard to get side effects. If there was a parallel version of if there were parallel sequential versions of a loop, we made sure that the sequential version was a little more verbose to encourage you to use the parallel version. Think about that. We purposely made temporary variable binding had the equal sign. If you wanted an actual assignment, you had to write colon equals. Just a little bit of an extra tax to say, yes, I wanted a side effect here, because we wanted you to avoid side effects in order to enhance the parallelism. And the third goal was to make a growable language. We didn't want to wire a whole bunch of features into the compiler. Instead, we set out to build kind of a flexible framework for building libraries. we didn't know whether the scientists would want complex numbers or quaternions or other stuff. So we built an object-oriented framework based on traits that allowed them to build their own libraries and made the syntax highly user-extensible. So we had a large team, sometimes as many as 12, 6 full-time and 6 interns, and this project ran for almost a decade. But we did not get the round 3 DARPA funding. That went to Cray and IBM. And once Sun did not get the round 3 funding, then they supported pieces of the project on a piecemeal basis. But the kind of cohesion of the hardware and the software and the runtime and the operating system kind of fell apart. And in particular, we had purposely designed an extremely ambitious programming language that we thought would require a 20-person team, in addition to another 20 persons building, in essence, a new JVM. And that new JVM, that new virtual machine, never happened. So here we were trying to implement Fortress on the existing Java virtual machine, for which the type system was rather bad mismatched and eventually got top-heavy. And by 2012, Oracle, which had taken over Sun, said, "You've had a good try, why don't you give it up?" And I said, "Yeah, that's a good decision." Okay, so we went into it thinking we only had a 20% chance of success. It was an ambitious project, and it did not pan out. And yet Fortress turns out to have had some influence. One is that the Fortress language specification has about 400 citations in Google Scholar. I don't know who's citing it, but people are at least paying attention to design and taking either positive or negative lessons from it. I don't know which. But I can say that one feature we put in Fortress seems to have made it the Swift programming language, which has to do with being able to bind variables in the middle of that statement. And then we let it sit fallow for about 6 years, and about 1.5 years ago I got an idea. I said, boy, we really hit our heads against that polymorphic method dispatch thing. I think I see a way through to the proof now. And it turned out I was mistaken, but I got Sik-Young Roo, who was one of my colleagues on the Fortress project, who was now at KAIST in Korea. And she and two of her students, a graduate student and undergraduate student, spent a summer looking at the problem with me. And it turns out that my idea wasn't quite right, but they found the correct path. And we now are going to have a paper in 2019 published about that on multi-method dispatch with multiple inheritance and variance in generic types. So that particular combination turned out to be a hard nut to crack. And so we got a paper out of it. So Fortress turned into something. Yay. So just to give you an idea what Fortress looks like, here's the mathematical syntax. We're not going to walk through the code. This is a sequential version of a very simple program. And it's got 3 loops in it. And I'll just point out that here I've got a for loop, and I say I want to go from k goes from 1 to n minus 1, and I want it to be sequential, so I have to say so. If I didn't say SEQ, then it would be parallel. On the other hand, I can just use parallel primitives, and the same program can be expressed much more concisely this way. And I'm not going to walk you through that either. But if this intrigues you, there is a Google Tech Talk video on YouTube, 4 solutions to a trivial problem. You can go watch that. Okay, last language I want to talk about is this thing called Augur. This is very recent work at Oracle Labs to develop a programming language to support probabilistic programming and machine learning. And this is work with these 5 other people. And the idea is that a program is more declarative in structure. It's a domain-specific language. And it declaratively describes a probabilistic sampling model. So for example, here's a whole bunch of, say, ACM papers. And I'm going to make a probabilistic model for these papers, and I say, these papers could have been written by enough monkeys with typewriters if only for each paper we had randomly chosen a topic, and then for each word in the paper we had chosen a word having to do with that topic according to a distribution of words associated with that topic. Okay, just sounds silly, but what you do is you make a model like that and say, now let's pretend that the papers actually were generated that way, and now let's run the model backwards and try to figure out if the papers were really generated in this way randomly, what would the initial parameters have had to look like? And this idea is known as topic modeling or topic inference. So given a bunch of papers, try to figure out what the topics would have been that would have caused these papers to be so similar and these papers to be so similar, but these 2 groups to be different. And so the idea of the Augur language, we would write a declarative descriptional model, and here's a sample of that. And then the Augur compiler would generate code that, given the observed outputs, would infer the hidden variables probabilistically, using methods such as Gibbs sampling and Markov chain analysis and so forth. And furthermore, Augur distinguished itself from some other projects of about the same time in trying to produce highly optimized parallel code for GPU execution. And we ended up having the fastest LDA Gibbs sampler around for that year. And we got a paper in 2014 NIPS. So that was fun. So, to summarize, I've given you a quick overview of my career. I like to read, I like to write. You'll notice I've highlighted all the papers I've written because I like publishing papers. I like finding out things. I like doing experiments. I like writing code, testing it, see how it works. But once I've discovered something, I want to tell the world. So I like to write. And why do I like to write? Because I want to give other people the joy of reading what I've read. Because I've so enjoyed reading what they have written. And I sort of, it's this two-way thing. I like to write, I like design, I like to code, in that order. My interests are broad. My central interests are about ideas and programming languages. But I don't care which programming language. I'm not just that Lisp guy. I don't want to be just that high-performance Fortran guy. I've tended to jump around from project to project. I usually have 2 to 4 things going at once, and if one thing stalls, I'm not stuck. I just work on other things until I figure out how to get unstuck. I've discovered that I do my best to work with a team. This is really hard for me because I'm an extreme introvert. And but it's worth it. I enjoy working with a team. It just takes energy. And then I need to hole up by myself for 2 hours, in my room and stare at the ceiling, and then I'm fine. Also, I learned by trying to be a manager, I'm not a very good manager. So in order to work with a team, I need to be a technical lead. I need someone else to be a manager of that team. It took me a while to work that out too. So I found a working and management style that works for me. Other people are good technical leaders and good managers, and they do both. Some people do technical stuff for a while, and they move into the management track and really succeed there. Looking back on my career, I found that I've kind of been the consummate dilettante. I often start something, identify some key ideas, write it up, and then let other people run with it. And that's fine. I'm very happy to let other people get most of the credit for actually doing the work of implementing. It's not that I'm afraid of doing that work, it's just that other people turn out to be better at it. Great, you do it, I'll go on and work on something else. Many times in my career, I don't know what to do, so I pick something and work on it. Like when I first arrived at Sun, I didn't know what to do, so I just picked something and said, okay, I'm going to study this. I'm not even sure if this is my range of expertise. I'm going to pick something, look at it, read papers about it, try to learn, and try to identify some place I can make a contribution. I often consult for another project, pick one thing I can help with, spend a week or a month beating hard on it, and then hand it back. So I function that way as a consultant inside of Oracle at this point. Not everyone works best this way. This is just me. So I've tried to sort of lay out a history of my career and what it looks like, hoping you can look at it and find something that will tell you what to do, whether it's I want to do the same thing as him or I want to do something different. Examine what I've done critically, figure out what works for you. Okay, so having laid all that out, I want to finish by giving you 2 homework exercises, because I've still got some professor in me. The first exercise I offer you is chasing down references. Pick a technical paper about a topic you really like. Get copies of all the papers at sites, read all their abstracts, then pick the 5 most important ones and read them all the way through and really understand them. Then recurse. That's the important step. Recurse. And you're going to have to prune the tree, and you aren't always going to be able to pick 5 out of every paper you run across. But the idea is to chase back through the literature and chase back in time until you feel you've developed a deep understanding of where the ideas came from and how they changed over the years. This could mean going back just 5 or 10 years. It could mean going 50. In some cases, it will lead you back. If it's a mathematical idea, you may go back several hundred years. When you're done, maybe you will be an expert on that topic. Maybe the global expert on the topic, if not at least locally, and you can serve as a consultant to other people there within whatever group you're working in. But this exercise of chasing down references is a great way to accumulate knowledge in a way that's concentrated on something you're interested in. And do this 2 or 3 times, and you'll get the idea. I found that harder to do for my desktop than working in a physical library back in the day when we didn't have computer terminals. I literally had to walk around the stacks pulling books off the shelves. But there's something tactical about it. But if you're disciplined, you can do it on a computer too. And this is not just a student exercise. This is something I do every month. Whatever I'm working on, I will say, okay, now it's time to chase down literature. I need to work my way back and find out what's important. And then you also need to try to figure out a way to find the papers that you missed following the reference chain, because sometimes some important paper didn't happen to be in that particular chain of references. Okay, homework exercise number 2, I would ask you to read a classic old paper. It could be any old paper, but in fact I have provided you with one. This is Tony Hoare's Hints on Programming Language Design. I have copies for you there. I was told there would be 41 people here. I brought 45 copies.
Well, this is for the PLMW attendees.
Yeah, these are for the attendees, the actual attendees. So this is Tony Hoare. This was actually his keynote at the 1973 POPL conference. It was the first POPL conference. It was held here in Boston, as it turns out. And so this is his keynote address. And here's one quote from the paper. If the purpose of a programming language is to assist in the documentation of programs, the design of a superb comment convention is obviously our most important concern. Okay, there's a very distinct claim. Now my question is, do you agree with that claim? In fact, what does this claim even mean? What does it mean to have a superb comment convention? And I had an idea in my head, and it turns out that his idea of a superb comment convention was very different from what mine does. I had done something very different in Fortress, for example. And those were both very different from what Knuth did with literate programming in turning text of the program into a published book. When you read this paper, I need to warn you about terminology. So here's a hardware thing. So here's a CPU and here's main memory, and they're connected by a bottleneck, a memory bus divided by a bottleneck. Okay, and you try to alleviate this bottleneck, what do? Well, maybe you put in a memory or two in between. And these are smaller, faster memories. So when the CPU wants data or instructions, it can go to these smaller, faster memories instead of way out to the main memory and get those things faster. Okay, so what do we call that? Caching, that's right. Okay, right. But this was actually introduced back in the 60s. This idea had to start somewhere. On a machine called the Atlas II, also known as the Titan. This is one of the Manchester machines down in the UK. And they were playing around with these ideas, and they decided to call the data cache the fast operand store, and the instruction cache is called the slave store. So I want to warn you that terminology is there in Hoare's paper, because the term slave store was actually current for about 25 years. It seemed to die out in the mid-80s, and I kind of tracked that through literature. And nowadays it's been replaced by cache, and I think that's a good thing. So nowadays we would say data cache and instruction cache. I have marked the 3 places in this paper where this occurs, so you won't stumble. I stumbled when I walked through and said, whoa, didn't remember that being there before, because I'd read the paper before. And I'd also like to warn you, there's another classic paper, which I'd recommend to you, it's about hardware design, about the virtual memory in the stretch computer. This is from the late 1950s. Wow. And when I first saw this paper, I said, wow, I didn't know the stretch computer had virtual memory. Well, that's an awfully early for that idea. Well, it turns out that what they called a virtual memory in this paper, we would call cache. Or a load buffer and store buffer. And you get cache is kind of a virtual memory. And that use for the words virtual memory died out and then got reused for something else when paging hardware came in about 8 or 10 years later. So the point is, terminology changes, and sometimes it's hard to read old papers. But it also raises this question, and here's the question I want to pose to you. How do changes in terminology reflect, or perhaps even cause, changes in the way we think about even technical things, especially when such terminology may involve anthropomorphic or social metaphors? How does that affect how we think about things? And this matters because programming language designers specifically are often charged with creating new terminology. So you want to think very carefully about how you choose that terminology and what it will mean to people. So I suggest that when you approach this paper, you read it critically. It's 45 years old. What still makes sense today? What would you disagree with in today's context? What would you have disagreed with if you were living in 1973? And of course that's hard because it involves trying to project your mind back into the milieu of the day. Does your favorite programming language today conform to Hoare's advice? And if they differ, is there a problem with language? Is there a problem with Hoare's advice? Make that judgment. What advice does not appear in the paper you think would be important to give to language designers today? What other questions does the paper raise for you, and how are you going to go about finding answers to those questions? So those are all things to ask yourself as you read that paper. But I think it has some things in it that still merit examination today for the contrast. So my last slide, what advice can I give to you? Don't do what I did. Don't hang around the local university hoping you can just walk in the door and get free access to millions of dollars worth of equipment. They lock all the doors now. I had some unusual experiences back in the day. But, look at what I did, and these are the things that I think I can abstract without getting too vague. Read long things, like book-length things, conference paper-length things, journal paper-length things. Read long things that have big ideas. Read science fiction. Read novels. Read about a variety of topics. Read stuff from different time periods, not just the last 5 years. And identify your favorite authors and seek out additional works by them. That was a very important strategy for me, both for computer science and for science fiction. Be curious and let that drive your efforts. Work with a team if you can, preferably including some people you can learn from. You want people who are better than you and some people who are maybe not as good as you. But the point is you want to be able to be in a situation where you're constantly learning. Volunteer. You never can tell what will happen. If nothing else, volunteering means that you're getting to do something that nobody else wanted to do, and therefore you'll be the unusual person. Maybe you'll find something that nobody else would have come across. Make it your aim to help others, and they'll help you. That's good generic advice. Don't be afraid to do tedious work if you'll think it will be productive. I'm going to point you to one more talk of mine, which is if you search for Steele 2017 Peapod keynote on YouTube, you'll find this description of a project I've been working on for the last couple of years, and I wanted to understand something about the development of mathematical notation in POPL papers. And in order to do that, I had to look at the mathematical notation POPL papers, and the mathematical notation is not captured by the OCR and the ACM's digital library, so I can't search for it. So there's nothing for it, but we actually eyeball every page of every paper in every POPL conference. And then I looked at some other conferences as well, so I ended up looking at about 25,000 pages of stuff. And it took a few months, but it can be done. And yes, that part was tedious, but by the end, I learned a bunch of stuff. So be smart. Don't do tedious stuff just because it's tedious. But if you think it'll be productive, don't be afraid of the tedium if you think something good's going to come out on the other side. Figure out what you are uniquely qualified to do and then do it. Several times in my career, such as with the Tickle compiler, I worked on something. I still thought it was interesting, but I saw that other people were working on it and I'm probably going to do it better, so I abandoned it. I try to figure out what I can contribute to the world. And maybe that's a good idea for you too. So that's the end of my talk.